So, in the previous few lectures, we had been concentrating on the various kinds of combinational circuits and how to build those combinational circuits using truth tables and simplifying them potentially using either the Boolean algebra axioms or the K-maps. And we, in the last few lectures, we have also looked at how to use K-maps to simplify the Boolean expressions represented by the truth tables. After that, we also took a brief detour and tried to see how this kind of circuits could be actually implemented using a simulator called Circuitverse. And you are encouraged to try out more number of circuits there, because this will give you a practical experience or an understanding of how circuits could be designed, and you will get a better look and feel of how these circuits look like, and you can see them in action, right? So if you are really enthusiastic about building this kind of circuits, you can always buy such integrated circuits and try it on a breadboard. But given that the medium of instruction here is online, we can typically help you with simulators and not really go into a breadboard level design. Okay, but if you are enthusiastic about this, you can always reach out to our instructors how to do it. They can at least give a basic idea so that you can get started. So, I will cover one more example. It's a very popular example that is there in many of our textbooks of a combinational circuit of a 7-segment LED. So, it's not really the 7-segment LED, but the driver for the 7-segment LED. So, let me first define what this 7-segment LED is. You have come across this kind of displays, right, in your calculators, microwave ovens, or anywhere, right, wherever you have a screen that has numeric displays that looks like this, right? Let me first draw this. So these are individual segments, okay? So this looks like an 8, okay? But individually, each one of them is a separate LED segment, and totally there are 7 segments, okay? And these 7 segments, I can number them. There is, let's say, we call this one as A, this one as B, this one as C, this one as D, this one is E, this one is F, this one is G. There is no specific ordering. You can always take your choice and develop this driver. And often you might have a decimal point, right? So sometimes in a calculator screen, you also use a decimal point, 5.67 you want to write, right? So in those cases, you might need a decimal point, but for the time being, we can ignore that. In that case, it becomes 8 segment, right? So it basically has 8 different outputs associated with the output. So how do you want to display numbers? So as you can very easily figure out, or you already have experience with this kind of displays, let's say if I want to display 1, right? So if I want to display 1, the 1 could look like something like of this sort, right? Where this F and E are highlighted and these are off, right? There are these LEDs are existing, the segments are existing, but they are not lighted up, okay? Which kind of means that you want to supply logic low to these LEDs, whereas you want to supply logic high to the LEDs F and E, right? For example, this is 1 is somehow written like this. Let's say I want to represent 2, okay? So 2, all of you also know, 2 look something like this, okay? And the remaining LEDs are not lit up, right? So now if you see, A is lit up, B is lit up, C is not lit up, D is lit up, E, F is not lit up, G. Okay, this was 2. Okay, similarly you can do 7, right? So 7 can look like this, right? And the remaining ones are as usual not lit up. So in this case, A, B and C. This was 7. So you can do all of them, right? For example, 1 to all the way to 9. So I can just quickly write, this is 1, this was 2, 3 could look something like this, 4 could look something like this, right? I can also look like this. 4, 5 could look something like this, 6 could look something like this, 7 we have already drawn, 7, 8, right, 9, right. You can also have 10. No, you cannot have 10, it's 0, so 0, right. Yes, sorry, so I think I made a mistake for 3. This looks more like E, sorry. So what it should be, the other way around, I guess. Okay, this is 3. So apart from this, you can also have some characters that could be displayed. Okay, so for example, if you want to display A, right, this could be displayed like this, A. If you want to display B, B might become very much like 8. So instead of having capital B, you can have, let's say, a small b. So this could be B. So similarly, you can have C. Okay, so D might start looking like 0, but we have to see how it can be done. Maybe in this way you can have D, right? E could be something like this. Okay, similarly you can have F, right? So likewise you can have P, for example. If you want to make P, you can make S, right? S is very much like your 5, right? You can have I is like 1. So if somebody asks you how many such patterns you can create from this 7 segment LED, what would be the answer? You can think every LED can either be on or off. So what is the total number of patterns that you can design from this 7 segment LED? So the answer is very simple. It is going to be 2 per 2 choices per segment, right? So we have how many segments? A, B, C, D, E, F, G. You have 2 choices. Then for that you have 2 choices, which is equal to 2 to the power, the number of segments that you have is equal to 128. So there are only 128 patterns that are possible using this, right? And it might not be the case that you need all 128 patterns for your application. For your application, you might be just requiring 1 to 0, right? You might be creating a digital clock, and the clock does not require anything other than 1 to 0, right? The seconds place or the minutes place or the hours place. If you want to adjust, trigger an alarm or set a stopwatch, whatever be it, right? It is only going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then again going to be 0. It's very much like the BCD, right? Binary coded decimal number. Okay. If you really want some kind of alphabets, you can also design it like that. For example, I give a specific use case. For you want to display the soft drinks in a soft drinks vending machine. You want to display, let's say, Pepsi, right? So this can be also made P, then I want to have E, right? Then you want to have P, S, I. Okay, this kind of display could also be done, right? Or if you want to show, let's say, Coca-Cola, right? C. See, all of these things are possible. That is why it is a very nice circuit that we can learn, right? Similarly, you can also have cola, C, O, L, and A. Okay, so like this you can see what are the different possibilities. So now let us understand what exactly is the 7 segment LED driver. Okay, so first you need to decide, you need to decide on the total number of patterns that we want to display. Okay. So if you just want to display 0 to 9, then you basically have this 10 kinds of things that you are interested in. If you want to only display 0 to 7, then it's just you only want to deal with that, because depending on the number of patterns you want to display, your input size has to be mapped to that, right? Your inputs, the number of inputs will also be the same, right? So you have to determine how many bits you want as an input, what is the size of the input in terms of bits, so that it can produce that many variations. Okay. So typically this display drivers is going to provide some control signals to this circuit, right? Suppose this is your 7 segment LED device. So this device is very simple. If you want to, so these are just the lights we have here, right? There are totally 7 lights or 8 lights including the decimal point. So apart from that, you have this control inputs. Okay, so the control inputs are going to be corresponding to A, B, C, D, E, F, G. So for now, let us consider 7. So A, B, C, D, maybe E, F, and G. So A, B, C, D, E, F, G. So this is the totally 7 bits that are available, and here we have to design a circuit which is called the driver. So the driver is going to output this 7-bit bus, which is going to internally contain A, B, dot dot dot, G. Okay, this is going to have the logic which is going to light up all these corresponding LEDs based on your demand. And you also has to have an input bus, but we do not know that how many bits should be considered in the input. That depends on the problem. Okay, so let's say we take up a problem where you want to display 0 to 9, right? Or we can take a small example just to make it simplified. So let's say we want to only display these 4 characters, right? P, E, S, and I, right? So in that case, what will happen? We will basically draw a truth table, and we will see. Let's say I specify the problem as follows. I want to display P or E or S or I, right? So apart from, other than this, we don't want to display anything else. Okay, so there are only expected. So using this driver, you can actually write the word Pepsi, right? Or any word that involves PESI, right? Anything that will include any combination or permutation of these words. Okay, and of course you need to have multiple LED segments to show multiple outputs, but for the LED driver is not going to change. So because you are restricted to only 4 outputs, how many bits should you require to encode them? Log 4 to the base 2, which is 2. Only 2 bits are required. So if I have these inputs as, let's say, X and Y, right? And the outputs are going to be all the 7 outcomes we need to see. So the outcomes will be A, B, C, D, E, F, G, because you need to have a mechanism to light up all those LEDs somehow, right? So let us again rename them so that, or name them, because in this slide we do not have that information. This is called A, this is called B, this is called C, this is called D, this is called E, this is called F, and this is called G. Okay, so now and I want to say that, okay, this is a symbol that I want to showcase. I have these options 0, 0, then I have 0, 1, then I have 1, 0, and then I have 1, 1. Okay, there are 4 different things, and corresponding to that, maybe I want to show P, I want to show E, I want to show S, and I want to show I. Okay, so for 0, 0 in the circuit, if you look at the last slide, I am basically defining this combinational logic logic for this particular set of inputs and this particular set of outputs. So anybody who gives 0 0 to the input, A B C D E F G H should be configured such that it displays P. Okay. So what should be the values of A B C D E F G H for E F G for P? So we can just see that C and D, apart from C and D, everything is 1, right? So C and D are going to be 0 0. So C is going to be 0, D is going to be 0, but apart from C and D, everything else is going to be 1, right? If I look at E, B and C are going to be 0 and 0, right? If you see E, B and C are off, right? So B is going to be 0, C is going to be 0, and we are going to have let me choose a different color, 1 1 1 1 1. How about let's say S is going to have, see, B is missing, right, and E. So B and E are going to be 0. Okay, so here also B is going to be 0 and E is also going to be 0. So we are going to be left with the others which are 1. And last but not the least, which is I could either be BC on or FE on. Let us choose F and E is on. It is completely your choice, right? So I want to display F and E. That could be one possibility, or B and C is on. Let me choose F and E is on. Okay, if F and E is on, nothing else is on, so I'll put a 1 and 1. So F is going to be 1, E is going to be 1, everything else is going to be 0. Okay, so 0 0 0 0 0. Okay, so now as you can see, I can derive the combinational logic for each one of these LEDs as a function of xy. Okay, so if I really want to have a circuit that does that, let's say A, right? What is the value of A? So I can very easily see that A is equal to 0 when x and y are 1 1, right? Which is very much looks like a NAND gate, right? If it is an AND gate, it would have been only this would be 1, but this is NAND. So it is x dot y bar. If I look at B, what is the value of B? The value of B is x bar y bar, right? X bar y bar or x plus y whole bar, right? So x bar dot y bar, which is nothing but x plus y whole bar, which is an OR gate. If we look at C, what is the value of C? The value of C is 1 0. So the mean term 1 0 is this x and y bar. What is the value of D? The value of D is if they are unequal, 0 1 1 0, then only D is 1. So which is very much like an XOR gate. You can take X XOR Y. What about E? E is a little bit so apart from 1 0, rest is there, right? So it's x bar y bar plus x bar y plus xy, which is equal to x bar plus x bar plus xy, right? So this is x bar plus xy. This is going to be the output of for E. For F, we can see that everything is 1. So F is going to be 1. That would be easy. And the other one is G. For G, we are going to have, let me write, for G, we are going to have x bar y bar plus x bar y plus xy bar, if I'm not wrong, right? So here you are getting x bar into y plus y bar, so it becomes x bar plus xy bar. Okay. So this could be further simplified. Okay, you can try it out as a gate. We can implement them, and maybe you can just simply use this Circuitverse to implement and see. Okay, to whatever we have done till now, we can simply try out these individual elements and create the circuit, and then give the respective inputs and see whether they work or not. Okay, so there they have one convention. I think they I'll just keep this thing right, and then go to the Circuitverse web page. So here we have these two inputs. Let us quickly define these two inputs. Yeah, this is 0 0 0, the x and y, these are our inputs. Our output has to be shown in a 7 segment LED. So this is our 7 segment LED, and these inputs has to be kind of mapped out properly. So let me quickly, because they might not be using the convention that we have A B C D F G, they might have a name, so we can quickly check the their convention. Okay, so this convention needs to match. So I'll quickly write down. The top part is M, TL, T and TR. So M is the middle, TL is top left, T is top, TR is top right. Right, so this is M, TL, T and TR. Right, M, TL, T and TR. These are the so this is our T. Let me do a mapping quickly. Let me go to this slide and then try to see, drag it to the side. Okay, so A, T, TL, TR, M, and BL, BR, B. Okay, D is not there. Okay. Okay, so we need to be a bit careful about this inputs. So M, we have M, we have TL, then we have T, then we have TR. On the bottom we have BL, B, BR and D. D can be ignored for now. Okay, so we have to just find out the correspondence. So T is nothing but A, TL is top left, which is nothing but F, M is G, middle, M is G, top right is B, bottom left is E, bottom left is this one E, then bottom is D and bottom right is C. So we have our mapping done, right? So this is the mapping that we are going to follow. So now let us implement the circuits one by one. So we will go with M. M is G. So this is X bar plus XY bar. So we will take a we'll basically create the mean terms first. That is much easier way to go, or maybe, yeah, I think we will do that. Or we can just do individually, right, to understand it better. So G was X bar plus XY bar, so we'll call it X. It is easier to identify. We will call this one as Y, easier to identify them. We can put these levels, and then we can just start using these gates. So here we have directly X, and this is going to give us XY, X bar. Okay, so now if I want to create the first input, which was X bar, I guess, X bar plus XY bar. So X bar we can directly take, and then we can put an OR gate. This is X bar, and then we'll have XY bar. So we will take Y, we can take this also, and we can put an AND gate. So this becomes xy plus xy bar, x bar plus xy bar. So this is an output. This output was meant for G, I guess. Yeah, so G is the middle one, right? So G is the middle one, and G appears on the first input. So this was the M. So you can put it like this here. As you can see, I mean, we'll see what is the mapping. Based on that, it will come. Then we can do something simple. F is 1, and F is going to be the top left, and top left is F here. As we can see, this is going to be always 1. So input that could be always set to 1, that is F. So like this we can control. So F is done. Next we can look at A, or yeah, M, TL, then T. Top one, top is A. A is X and Y NAND. So we have X, we have Y. We'll basically put a NAND gate. So this is our NAND gate, and I can put Y as one of the inputs, and I'll also put X as one of the inputs, and this is going to be the output for the next one. Okay, then we will look at the next thing, which is B. B is X plus Y whole bar, and B is the top right. So let us see if we have a NOR gate. Yes, we have a NOR gate. So this is again this one, and this is Y, and the output goes here. So this is your yeah, it shows something. So we are done with the first top, the 4. Then we have 3 more, which is E. E is X bar plus XY, and D is X or Y. So D you can quickly do. So D, it's an XOR operation. So we will do get X, we will get Y, and the output goes to D. So D is the bottom one, right? So second one from here. So D will go here. This is D. Then we have one more, C. C is XY bar. I think XY bar we have already created. So this is X and Y bar. So this is directly going to be fed here, right? And then we have only one remaining. The remaining one is E. E is X bar plus XY. So XY could be directly available here. So we can make it this here. We can make XY out of it. This is X, this is Y, and this is your XY, and we need to put a OR. So this is our OR gate, and we want to do I guess X plus or X bar plus. So we have output of X bar here. So we can also drag this X bar and put it here, and this goes to the first gate. Okay, so we have to just check whether there might be some minor issues. Just need to make sure that everything is fine. There could be short circuits and so on. Okay, so now we had 0 0, which is basically resembling the pattern P. Okay, that is our agreement, that 0 0 should look like P, 0 1 should look like E, 1 0 should look like S, and 1 1 should look like I. So if you put 0 0, it looks like P. Then I have 0 1, which looks like E. Then we have 1 0. 1 0 should look like S, but there will be some kind of a mistake probably that we have to see. The first were correct, but it does not quite look like S. So I think there is something missing in the circuit. And then we should have 1 1, which should again look like I, but we have to just correct it if there is something wrong, right? So we have to debug that definitely. Maybe there could be some wiring problem. There is one more way to do this. So you can always do this combination analysis here. That will automatically generate. So this could be done, probably some debugging has to be done. Maybe there is some wiring that is wrong. I am doing it real time now. But if I put X and Y as inputs and put, let's say, A, B, C, D, E, F, G, this could directly be, just a minute, I've probably done something wrong here. Oh, there's a comma has to be given, A, X and Y, and then if I create A, B, C, D, E, F, G, this can create the truth table directly. So here I have to just use the values that we were putting earlier. So this is C and D are 0 0. So C and D are 0 0, rest are 1. This could also create the just the mean terms and then add them. Then in the next expression, B and C are 0 0. So B is 0, C is 0, 1, 1, 1, 1, 1. Then for the next one, B and E are 0. So B is 0 and E is 0, rest are 1. Then the other one is all are 0 except E and F. So E and F are 1, rest are 0. So this can also generate a circuit, right? It basically uses all the mean terms, right? So yeah, this could be another way that you can also create all the mean terms and then directly put a 7-segment LED here. Just that the A, B, C, D conventions has to be followed. Here we were using basically the G is first, G, F, A, B. So first is G. So GC is the first one, G. Then we have, I think, G, F, A, B, right? So G and then F. F has to be dragged out. This is F. Anyway, there might be, if there are issues, I will revisit this and then try to give you a working circuit, because real time sometimes there are some issues that we have, G, F, A and B. So the next one is A, which is pretty much the same that we have also done here, A, and then we have B. So this is G, F, A, B, and then we have in the bottom E, D, C, right? So we have E is the first one, then we have the second one, which is D. This is D, and then we have C. So P has already been formed, as we can see. Okay, so here it is 0 0, then we have 0 1, which is E, then 1 1 is I, and 1 0. I think here also there is some wiring issue. That is the reason sometimes some wires are not connected properly. That's why. So we have to really debug and see what exactly there is a misconnection or loose connection. It ideally should have given 1 0 should be S. We can double check the truth table. So this is how we should do, right? This is how we should do the design, unless and until my truth table is wrong, which could be the case also. So in our truth table, let us go back and see what is the issue. So S was 1 0. 1 0 means this is off and this is off, which is B and E are off. Okay, so B is 0 and E is also 0. The rest are on, right? So A, C, D, F and G are on. So I think this is what we have also reported in the truth table, but I think this is purely an implementation issue where there might be some mistake that I have done while connecting the wires, right? So I will definitely make sure that we are going to give you a circuit file that works and you can test it out. I would also encourage you to do it yourself. So sometimes you can do the simplification on your own and do the circuit like the way I have done, or you can actually have a complete decoder and do it yourself here. You can simply define the truth table, and as a combination analysis part, you can define the number of inputs that you want, define the number of outputs and the output names and the input names, and this is going to automatically generate this SOP expression, right? As you can understand, this is an SOP expression. You have the different 4 min terms, right? And then apart from that, you can also, from this min terms, then you can create anything that you feel like, right? So you can take ORs of these things. So you have a 2-level circuit. The first level is your AND level and the second level is your OR level. You get all the different min terms and then these are directly supplied to the 7-segment LED. Okay, so there might be some glitches that we will. So here I works correctly, P works correctly, E works correctly, but there are some glitches in S. So S ideally should also have this particular thing colored up, right? So then it will become S. So I think all of them are correct except the middle bit, right? The middle bit should also glow. There is some only issue with one particular LED, right? Otherwise this looks reasonable. Okay, so this can be corrected and I will make sure that you have the correct file. So you can practice more using the Circuitverse website, which is really helpful in cross validating your design or get some actual practice. Okay, so I'll stop here.